Hello, I'm Neeraj. Today, in this part of the tutorial, I will try to explain about bit versus qubit and some basics about qubit. Because without getting such kind of qubit related basics, you will not be able to convert the real life classical data to qubit data, which is actually used by all quantum circuits. And finally, you will not be able to design the quantum deep learning systems. So this part is very important and crucial. Generally, we say that there are in a classical machine learning or classical systems, we say that there are some problems which are NP hard and NP complex kind of problems. Means we cannot solve these problems in polynomial time or real time. This is because in the traditional system we use bit-based systems like 0 and 1. So we do a lot of binary computations in the sequence. We may achieve some kind of parallelism, but it has some limitations. But in the quantum system, we have advantage of using qubit system. So actually qubit system is a superposition of states. So if we take a very basic qubit system, just one state system, like one qubit system, then we can represent it like now if we take the power n, then parallelly we can run n qubit in the same system, and this improves the computation so many times compared to the traditional bit system. Full parallelism we can achieve, near to full parallelism we can achieve, and that's why a lot of problems which are NP hard or NP complex is an polynomial time or real time solvable in the quantum system. For example, some cryptographic things, it is said that if you use the supercomputers also, then it will take thousands of years to break some cryptographic, especially public key cryptography, RSA encryption systems. It will take thousands of years. But through quantums we can break it in seconds and minutes just because of these parallel computations. Okay, so let us go into the more detail, like how we represent the qubit, how we compute the representation states, so that we can use it in the circuit design. So the basic of qubit system is one qubit. So one qubit contains 2 to the power 1 equal to 2 states. So here you can see that this is an example of one qubit. So it has 2 states. Now you will ask that what is this alpha 1 and alpha 2? So this alpha 1 and alpha 2 are actually coefficients. We say it as a probabilistic distribution of states. Here, due to this, we have condition that should be equal to 1. Even if we have multiple such states, the sum of square of all such coefficients should be equal to 1. Okay. Now you will see that what is the meaning of this, what this state represents. So you already know the one hot encoding. So suppose we have 2 bit and you know some little electronics or one hot encoding. Generally you understand that we represent it like 0 and 1. Now for 0, we see that 0 is present here. So in one hot encoding, what you do? You will write 1 here and 0 here. So now we can transfer this like alpha 1 and then vector 1 0 plus alpha 2. Now 1 is there. So what you will do here? So here we will use 1 and here we will use 0. So it will be like this. When we solve it further, it will be equal to alpha 1, alpha 2. Do you know what we say this? We say this as a superposition state vector. So it gives the superposition states of both, like what may be the occurrence of this state, what may be the chances for this state. That's why we say this as a superposition state vector. Now you may think that what is this notation, like some line and then greater than sign. So what is this? Actually, what happens in the quantum field, we generally use two different kind of notations. So first notation is known as Qubit notation. We represent it like this. Actually, it represents the d-dimensional column vector in complex space. Why we say that? Because these are actually the member of some complex numbers. That's why we say that we represent it in a d-dimensional column vectors complex space. So we have already seen that we represented it like 1 and 0. So this is the representation. Another notation that is also used, this is called Bra notation. So we use just a conjugate kind of notation, just keep it here, then you will get the Bra notation. Definition is also same. It is d-dimensional, row vector in complex space. So in this case, the Bra notation for this will be 1 and 0. Actually, the Bra notation of any state is the conjugate of equivalent state in the d-dimensional and equivalent state in the Qubit notation. And other thing is, if you want to know, get the Hermitian conjugate, we are not going into that detail. If you are going, suppose you want to go to Hermitian conjugate for Bra notation with respect to given Qubit notation, then you have to take the transpose of that vector. And for you have to calculate the conjugate, complex conjugate of each of those elements. So what is known as complex conjugate? Suppose we represent C as a complex numbers a plus iota b, then its a complex conjugate will be equal to a minus iota b. So that two operations you have to do on the data. But here we will just go through the Qubit notation only for simplicity. Suppose we want Q2 qubit, then we will have total 2 to the power 2 states. means 4 states. We can represent it like 0 0 0 1 1 0 1 1. Okay. Now our entire data will be represented as alpha 1, this is like, here again we will apply same principles are applicable for all those coefficients. Now how we can convert like a superposition state vector for this? So according to the quantum concepts, we can take the tensor product of two zeros, first and second. Same we will do with everything. So what will happen? So it will be like 1 0, we will have a vector tensor product 1 0, and when you solve you will get 1 0 0 0. Just multiply and check, because this is a simple multiplication, anyone can memorize. Now the next thing is you can connect it with one hot encoding. Very simple. Take the step 0 0, it is here, so here it will be 1, other places will be 0. So this is same thing we got, so we can write it like 1 0 0 0 plus alpha 2, again for 0 1, here it will be 1, so 0 1 0 0, again alpha 3 0 1 0 0 1 0, for alpha 4 it will be 0 0 0 1. So if you solve this, you will get this alpha 1 alpha 2 alpha 3 alpha 4, just matrix addition. So this is again superposition state vector. Now you may ask questions like every time we will not get all the 2 states or 3 states. So what will happen if we get only few data with only few states, like this type of data? Suppose we get like 0 1 1, sorry, alpha 1 0 1 1 plus alpha 2 1 1 1, we get this. Now how we will get the superposition state vector? Very simple. Just to try to understand that this is a 3 qubit system. So we will have 2 to the power 3 equal to 8 states. Just try to identify which may be the 8 states. So these are the 8 states. So instead of calculating tensor product or anything, you can directly take this reference. So 0 1 1 is coming here, and 1 1 1 is coming here. So it will be equal to like 0 0 0 1 0 0 0 0, and it will be like last position. So when you solve, you will get 0 0 0 alpha 1 0 0 0 alpha 2. So this is the superposition state vector. Now you may ask some questions like why we should enter only 0 1 type of value. Suppose we want to enter something angular, then what will happen? Suppose like this. This will also work, like cos theta 0 plus sin theta 1. It satisfies these functions because cos square theta plus equal to 1. Now we say that okay, no, we will take something different. Will it work? Yes, it will work. For example, we say no, we will take this. Here, this is our coefficient. So again, it will work. So it is working. Now you may say that our data is not look like this. Our data is like this: 0.336, 0.378, 0.89, like this. Then what we will do? For that we do generally some angular rotation. We take the radian and then first we normalize the data into 0 to 1 format and then take the angular rotations. For that we have to understand some gates to do those angular rotations. So once we apply those angular rotations, it will convert the data into Qubit system. Now you are ready to switch from Qubit system to quantum circuit. And after quantum circuit, I will try to explain how to prepare one basic quantum deep learning architecture.